The next thing we need to talk about is organic acids and bases after reviewing the Bronsted acids and bases theory. There are different organic compounds, as you know, but we focus on these four categories for the moment. We are talking about alkanes, then alcohols, carbonyls, and carboxylic acids, and study their acidity a little bit based on their structure and what happens during an acid-base reaction. So, in these types of compounds, we have in alkanes. Let's talk about alkanes. We just have single bonds between carbon and hydrogens. And I'm sure you remember from general chemistry that any combination of carbon and hydrogen is called the alkyl group. So instead of creating a compound and put a different number of carbons and hydrogens, let's just imagine they can be any combination of carbon and hydrogen, so we call them alkyl group. Now, in reaction with water, oxygen, which has enough electrons, it will grab the water, so it will act as base, and alkane will act as acid. Because hydrogen cannot form more than one bond, then the electrons will move over the carbon atom. So the product of such a reaction will be a non-bonding electron pair with a negative charge, and we also have the hydronium ion. Now, if we want to talk about the acidity of this group here, this anion, carbide, it's called carbide. This anion does not have, it's not strong. So it's not a stable anion. So why? Because the negative charge on carbon is not a good thing to have. Plus, there is no stabilizing effect. So alkanes are not strong acids. As we go down the list, you will see the difference between good acids and not strong acids. Let's move towards the alcohols. Alcohols, as you know, have OH functional group. So oxygen grabs their hydrogen again because they're supposed to be acids. And water is going to be the base, and then electrons will move over oxygen. Plus H3O, hydronium ion. Comparing to when negative charge was on carbon, negative charge on oxygen, which is a more electronegative element, is somehow better, but still alcohols are not very strong acids, but better than alkanes. Now, we get to carbonyl compounds. Carbonyl compounds are those that include a carbon-oxygen double bond, like acetone, the nail polish remover. Let's say we are using them as an acid and water acts as the base. In such a reaction, again, oxygen attacks any of these hydrogens, basically the hydrogen which is the most accessible. In this case, the value of all of these hydrogens are the same. So the bond opens on carbon. Because there is nothing happening on this carbon, allow me to save the space and just use CO, CH2, and their negative charge. Now what do you see? You see a source of electrons and a target. So this is the first time that we can have a resonance structure. Let's write the second resonance structure for this compound. Then you will see we have CH2. Now, going from the first resonance structure with the negative charge on carbon, which is not very electronegative, towards the oxygen with the negative charge, which is an electronegative element, we have two resonance structures, which resonance is considered as a stabilizing effect, and then we have even a more stable anion. because of negative charge on electronegative oxygen. So you can tell that carboxylic, the carbonyls are good acids. Comparing to alkanes and alcohols, they are good acids because the anion can be stabilized by the resonance. And finally, carboxylic acids, their name says that they're acids. So let's prove that they're really good acids in an acid-base reaction. It's supposed to act as an acid, and water is supposed to be the base. The same story. Oxygen, the electrons and oxygen grab hydrogen, the electrons remain on oxygen, and we will end up having two resonance structures, one here, and then we have a good source and a target of electrons. So put the resonance structure for the second structure. So you see, we have created resonance structures, and not only one but two strong, stable resonance structures, because in both of them, negative charge will be on electronegative oxygen. So they are very good acids because they have very stable anions. That's how you study the acidity of compounds. So we have to be fair, it's time to talk about organic bases. About organic bases, we talk about oxygen and nitrogen containing compounds, organic bases. Nitrogen, oxygen, and nitrogen containing compounds. So, let's talk about this compound. If nitrogen containing compound acts as a base, means it's going to accept the proton, right, from water. So if I draw my water molecule with separate bonds, then we'll see if this compound is a base, nitrogen attacks because it has non-bonding electron pair, and the bond opens on oxygen. Then we have NH3 with a positive charge, and if you're not sure about the charges, you just simply calculate their formal charge. Everything is, for the charges you see, are based on calculation of formal charges. So we have acid and base. The same story for oxygen containing compounds can happen. They can act both as acid and base. So depends on what they are reacting with. For example, if we have an alcohol and it acts as base, and water is an acid, so we will have base accepts one proton, right? CH3, OH2 with a positive charge. The one of the electron pairs is used to form a bond with one of these hydrogens. And you just saw when we were talking about organic acids that alcohols can act also as acids. So both nitrogen containing compounds and oxygen containing compounds can act as acids and bases depending on what they are reacting with. Now, we learned about these two categories of acids and bases in organic chemistry. It's time to know about the factors that affect the acidity of organic compounds. They affect the factors are, first, the element effects. By increasing A, which I'll just write down the title, element effects. So by increasing the size of A, let me go with a non-organic acid with some non-organic acids to show you how it works. So acidity increases by increasing the size of A. So if acid is HA, A is the anion, okay? Again, non-organic acids, let's compare hydrofluoric acid to hydrochloric acid, hydrobromic acid, and hydroiodic acid. So in which one, anion, fluorine, chlorine, bromine, and iodine, which one A or anion is larger? Down a group, the atomic radius increases, so HI is larger. So what happens is that the difference between the radius of hydrogen and iodine makes the covalent bond not very strong. So this bond can easily break. So by increasing the size of anion, acidity also increases. And this is the same for organic compounds. Depending on your anion, the larger the anion, the stronger the acid. The second effect is inductive effects. You remember the inductive effect, polarizing the bonds? Let's say you have RCH2OH and RCH2NH2. Okay? Which one of these, everything else is the same, but the nitrogen and oxygen are different, right? Which one of them is more electronegative? Further down across the period, further to the right, sorry, across the period is more electronegative. So oxygen is more electronegative. What happens? It pulls the electrons in the covalent bond more strongly towards itself. So we have a partially negative side on oxygen, partially positive side on hydrogen. Then the more the electronegative element, we will have a looser bond between that element and hydrogen. So the hydrogen will be released in the solution faster. That's what we refer to as acidity. So the more the electronegative element, or the stronger the electronegative element connected to the hydrogen, that hydrogen, the bond is weaker, the hydrogen is looser, and it can be released better. So comparing the nitrogen-containing compounds with oxygen-containing compounds have more acidic properties. The third factor that affects the stability of the acids or acidity is resonance effect. We just learned when we were talking about acids like the carboxylic acids are better than carbonyls, because like let's say you have RCOH with water. We had that in the previous page. So oxygen is going to grab the hydrogen, and we have RCOO negative. It's a good anion because a stable anion, because oxygen, electronegative element, carries the negative charge. And plus we have a resonance structure with the same stability because we have another oxygen that can carry the negative charge. So it's a good flow of electrons to form the stable ions. But for carbonyls, if you remember, we had CO, like CH3 plus water. So we have RCOCH2. This anion is not very good because it's not very stable because the negative charge is on carbon. But second anion can be better because the negative charge flows on electronegative oxygen. But still, comparing to carbonyls, carboxylic acids are better. That's what the resonance effect means. And the last one is hybridization effect. You will have this to be discussed more in the future. Let me just briefly tell you, like when we talk about hybridization effect, we can easily compare an alkane with an alkyne. For an alkane, the hybridization on carbon is what? You have 4 groups, all of them sigma bonds, so hybridization is sp3. So the share of S compared to P is 1 to 3, so it's only almost like 33% S, right? But for alkynes, if you have this structure, what would be the hybridization? 2 sigma bonds is only sp. So in sp, the share is 1:1 or 50% S. Why do we talk about S? Because remember, S orbitals are spherical. Electrons in S orbitals are closer to the nucleus. So the more the share of S orbital, the more the acidic property. So I want you to keep these 4 factors in mind to assess and compare the acidity of different groups. Let's work on one of these problems given to you in the bottom of page 5. You are supposed to rank them in the order of increasing acidity, from the least to the most. So what do we see here? We have 2 electronegative elements and no electronegative element. Between these 2 electronegative elements, which one is more electronegative? This one, right? So this is our number 1, acidic. Another electronegative element not as strong as oxygen, that's the 3rd one. And alkanes, you remember, are the last. So 3, 2, 1. 1 is the most acidic. Let's quickly work on this one as well, since we are finishing this page. So, effect of electronegative inductive effect. An electronegative element, no electronegative element, both of them are carboxylic acid, and this one is an alcohol. Alcohols don't have this oxygen, so between these 2, when we want to decide, because of the inductive effect, this is number 1, because no inductive effect, this one, and alcohols are less acidic than acids. So again, 3, 2, 1. 1 is the most acidic. And one more thing to remember, what page 6 is trying to tell you is that since we're still talking about the acid-base reactions, is that when we want to determine the direction of a reaction, when we have, like, let's say strong acid plus a strong base, and here we have weak acid plus weak base. We determine the acidic and basic properties based on what we just learned, or from Ka and Kb values. So the reaction always goes from the stronger side to the weaker side. So most of this reaction goes towards from strong to weak. Maybe a little bit goes back, but the reaction always goes from the stronger side to the weaker side, and it should make sense because the stronger acids and bases can dissociate, can ionize to weaker. But the vice versa, if we have weak acid and a weak base, then only a little bit of this reaction goes towards forming strong acid and strong base, and mostly goes back to the weak side, because the weak compounds don't have that strength to go to the strong side. So it won't occur. This one won't happen. but this one strongly happens. So if you add two weak acid and bases to each other, don't expect anything happen, or expect anything hardly happens. The last part of this chapter is about the Lewis acid-base theory. You had in the introduction of Lewis acid-base theory in general chemistry too, and you know that Lewis acid-base theory is the best acid-base theory that we can work with. It's the strongest because it's not about the hydrogen ions, it's not about protons, it's not about hydroxide ions, but it's about electrons. So just like the Bronsted theory, we need to know the basis of the theories for Lewis theory as well. So a Lewis acid is electron pair, not single electron, the whole pair. Electron pair acceptor is the opposite of Bronsted. So we say acid, accept. Okay? AC, AC. Acid, accept. And Lewis base is electron pair donor. So, we need to know what compounds can act good as Lewis acid, which compounds can act as Lewis base. Almost towards the second half of page 7 is extremely important to know. Extremely important. I want everyone to know and learn the second part. Which compounds can be good Lewis acids, or basically can accept the electron pairs? An atom with a vacant orbital, like aluminum, like boron, like gallium, like transition elements, they are good. So like you remember BF3 and AlCl3, they are very good Lewis acids because they can accept electron pair. They have vacant orbitals. Or hydrogen in a polar bond, when we say like HX and this is positive, this is negative, this side is acidic because it's partially positive, means the electrons are stripped off of hydrogen by the halogen, and it gives the chance to hydrogen to accept electrons. Also, we have cations. The cations also, of course, cations are positively charged ion, right? Like magnesium, like lithium. You will work with these two metals at the end of this semester. So keep in mind the magnesium and lithium are two useful cations in organic chemistry. And also we're talking about transition elements like zinc, like iron, like titanium. They are good acids in Lewis theory. What are good Lewis bases? Electron donors. Basically whatever it has electron, right? Most of the oxygen containing compounds and nitrogen containing compounds, because you always see electron pairs on nitrogens and oxygens, as we discussed. So as an example, still on page 7, you have aluminum trichloride, and we said aluminum is one of the elements that has a vacant orbital. Plus, if you add it to H2O, what happens? It can accept the electrons, so hydrogen is the electron pair donor, so we have the base, Lewis base, and aluminum trichloride will be the Lewis acid accepting the electrons. Here we don't have the conjugate acid base. Conjugate acid base is only for Bronsted theory. So you have this, of course, oxygen has used the electron pair to form the bond, and aluminum is accepting. So don't forget about the formal charges. The last page of this study guide is about more practice on both Lewis and Bronsted theory. Like HCl is a polar bond, right? So this is our Lewis acid plus. So what happens is that's why oxygen always attacks hydrogen and kicks the other atom out. So we have H3O with a positive charge. Just calculate the formal charge of oxygen. It will turn out to be +1. Plus we have chloride ion. So it would be acid, it would be base. The second one is very similar to what we worked on, aluminum trichloride and water, so I skip it. This next one is CH3COOH plus CH3COCH3. So let's determine the products are given. So just need to determine the acid and base plus so seems like this hydrogen has been taken away by this oxygen. So this is partially negative, this is partially positive. So hydrogen will be our acid and this oxygen will be the base. So what we end up having those products, and I'm sure you can work on the last one, very similar to what we worked on now. Oxygen has always the lone pair of electrons, so even if you don't see them, make sure you put them. So you see, seems like the hydrogen is added here, so this oxygen has attacked and electrons remain on oxygen. So which one is acid, which one is base? You can work on both Lewis and Bronsted theory. So seems like this is partially negative, partially positive, and hydrogen donor, hydrogen acceptor. So we have base, we have acid, and based on Bronsted theory, this is going to be the acid, this is going to be the base. If you want to discuss it based on Lewis theory, you would say this is the electron pair donor, so it's going to be the base. This is going to be electron pair acceptor, so this is acid. Basically, anything you can answer, any questions you can answer based on Bronsted theory, you can definitely answer it in Lewis theory. I hope this review was useful for you. Please make sure you have enough practice on the end of chapter problems and your assignments, and feel free to ask me your questions.